And what you will see is you indeed get the Coulomb's law for this this magnetic monopole. And actually one can go even further and derive the Lorentz-Force law for the magnetic monopole, which is Qm G mu nu G mu. There might be some factors, but G mu nu here is the hot joule of the F mu nu. So namely, it is epsilon mu nu rho sigma F rho sigma, and it reflects the fact that if you observe that we have this minus sign here, so the Lorentz-Force law is actually Qm minus B minus B plus B times C squared. Right, so yeah, if you go and calculate, you'll get that. And so given that our artificial magnetic monopole has so many properties in parallel to the electric monopole, it actually might tell us something very exciting, which is maybe the physical monopole, i.e. the electric charges, maybe it's not as fundamental as we might think. It might be a result from this construction as well, namely, you have a very dense field in the form of a string, and when you do all this calculation, it just turns out to be, point-like. And so it might mean that maybe the most fundamental object in this nature is actually a string-like object, but not point-like, as we might put. And yeah, so that was the end of my talk. Does anyone have any questions? Sure.
What if that? Come on. Well, what if that solenoid is perpendicular to the direction of motion?
Which one?
Sorry, that example.
This one.
Yeah, what if it's perpendicular? So
it doesn't have to be. It can So the first one is this. The second one is that. I mean, it can lie anywhere and in any direction you like.
Oh, what if you're lighting like this plane?
You mean the
YZ plane?
what? Sorry.
YZ plane.
YZ plane. Here.
Yeah.
You mean the surface there?
Yeah.
Or the solenoid?
Yeah.
The surface that lie in the YZ plane, yes.
Yeah. So
but the solenoid itself doesn't have to.
what if it lies in the YZ plane? Then do we still get that kind of constantly, or not, Lorentz magnetic charge?
I think so.
How do we show this?
I think so because
without any continuity argument.
Okay, sure. So I mean, the B field in the Z direction is going to change, right? It's going to be gamma times B in the Z direction, but then the surface gets contracted by the 1 over gamma. This is the surface area, so it's the same.
Cool.
Yeah.
Do you have any other questions?
Sure.
I'm not 100% sure why are you assuming that the string is not observable, because your whole construction rested on the string being there, right?
Yeah, I mean, I'm not saying that the string is not there, but if you can't see, if you can't observe in anywhere, in any way, that the string is there, the only information, I mean, let's suppose, okay, you have the string, right? And you know that the field everywhere not on the string is point-like. And if you imagine that suppose you cannot observe the string, what you will see? What you will see is only this point-like field. You will see some field like this, right? And then you try your entire life and then you don't see the string. What are you going to say?
Why are you making that assumption? I don't understand it, because your construction rested on the string being there. So why are you not saying that?
Yeah, I mean, the string is being there, even though it's not observable. It is there. It's just the case that we cannot observe it. Because if we can observe it, we will know that this is not a magnetic monopole that we want. Just like the electric monopole. you never saw the string of electric monopole, right? And when you see this field from the electric monopole, then you conclude that, okay, it's some point-like object at the origin of our coordinate. And so it means that if you see the string, you know that it's not a monopole. So it must be the case that if you want it to be a monopole, you have to be not being able to observe that string. It doesn't mean that it's not there. It is there, but you just can't observe it. It's just like we have an A, the magnetic potential. It is there. You can't observe it. You can only observe the magnetic field.
You can get away without having a string at all, right? You can just define. The point is that you could. I mean, your A, as you say, isn't defined on this string going downwards.
Yeah.
But you can construct another A, which is defined everywhere but at the north pole.
Yeah, but
and the difference is a gauge transformation.
Yeah, so it is. So actually, we can do something like that as well, the patching and this sort of thing. It turns out that the gauge transformation is corresponding to you move this string around, but then strictly speaking, you change the field because the field gets there. And if you move the string, you change the field. So it's technically not a gauge transformation. But then if you think about the physical thing that you can do or you can think of, then it must be the case that this is not observable.
Wait, so the string is gauge dependent?
The string is not gauge dependent. Okay, let me say this. You remember this A field, right, at the beginning? You can change it by a gauge transformation to this field. And the gauge function is something that is proportional to phi. Now you might call this gauge transformation. It is in one sense, but then if you want to strict the gauge transformation for the transformation that actually leaves the field untouched, this is not a gauge transformation. And the reason is this is not a function, it's not single valence. So what I'm saying is that if you do this, the so-called gauge transformation, you actually change the field, so it is not a gauge transformation. The string itself is gauge invariant, so it's not dependent on the gauge. But when you do this so-called gauge transformation, it is corresponding to moving this string.
So is it like a classification which gauge transformations are allowed?
Yeah. But then it gives you another problem if you want to do this integral, right? You do need the gauge transformation to be a function, otherwise you get more term when you do that. And you know that you shouldn't get that. And actually, so according to what Roland say, if you do this, if you accept that this is a gauge transformation and you do this, you get another contribution, which is not the same as the original B field. And then what you say is, let's say that we can observe that quantumly, and then you arrive at this condition anyway. But I chose to present this thing because it's the most physical one. Because you don't need topology or, cohomology or something like that in order to understand.
It's a beautiful story in terms of geometry, which
Yeah.
allows you to do this.
Yeah, we need more mathematics to do. But this, you only need integration, elementary integration, and elementary electron.
Are there any other questions?
And you were going to ask something?
Yeah, I thought there was
Oh, no.
He's just looking at me for some reason.
Okay, sure.
Okay, super. Thank you.